Well, greetings once again, everybody. Um, my name's Lee. This is lesson 14, Trigonometry for Students and Surveyors. We left off, we ran coordinates around this polygon last couple of lessons. I've taken all the coordinates off, all the bearings. Oh, that's the other thing I wanted to say is I watched my own video and I inadvertently call bearings azimuths bearings or angles. It's just I was in the habit of at older data collectors, everything was bearings, but it's actually, these are azimuths. Well, these aren't azimuths, these are angles, but these are azimuths in here, and I called them bearings, azimuths, and angles. I noticed, so they are an angle if you want to look at it, because we're doing rectangles, and this is the hypotenuse. These are all the hypotenuse. Bearings, very similar to azimuth, but we've already gone over that. One thing we didn't get to do is reduce or check our angular error. We did, and we ended up with the right angle and everything. We're good on that. But we, in earlier lessons, we talked about how a triangle has three corners, and those add up to 180 degrees. And the formula is the number of angles minus 2 times 180. So a triangle has 3 minus 2, that's only 1, so 1 times 180. So now you get to a polygon like this. This represents a traverse, and we have 8 angles, and then so we want to go minus, these are interior angles too, by the way. These are all interior angles, and they're all right angles clockwise. These would be exterior angles, and of course whatever this one is, if you subtract 360, you're going to get that one there. You're going to get that exterior angle. Same here. So we have the number of angles is 8 minus 2 times 180 is 1080 degrees, minute 0 and 0 0. And like I said, your exterior angles are the number of angles plus 2 times 180. So that's how you would calculate that. And what we're going to do now, we're going to grab the calculator, and we're going to, so a good traverse, a good surveyor, or just for your math students, your student geometry, trigonometry, you need to know how to reduce your traverse and check your closing angles. The closing angle on this one was this one here, because we started here, we came all around, sat here, checked in here. We had a good check in, only a few thousandths. That's the other mistake I made. I kept calling it hundreds, but it was actually 12 10,000ths by 8 10,000ths. If you were going to look at the precision of that, I forget what that hypotenuse was. You divide the entire length of all these legs by your miss, and that's your precision. And it's going to be, this one was like 1 in a million or 1 in 2, so way super accurate, and it should be. Okay, so we're going to add these angles up. So you want to calculate our angle. We've calculated them there. That's what it's supposed to be. And as a surveyor, we're always trying to chase that 0. We're always trying to chase the residuals right down to 0, and that requires very good equipment, very well calibrated. Your tribrachs, your prisms, everything calibrated, set up perfect, and that's what you strive for. And if you're a geometry student or trigonometry student, same thing. You're always trying to get this math to work out perfect, because it's math. You do the best you can. Okay, so we're going to just go through this. I'm going to sit down, get comfortable, and we're going to go through these. And there's a couple different ways to do these. I was showing you how store, now I don't want anybody to get confused, but I was going store plus 7 last time and store plus 1. Those are just the keys. I wasn't adding 7. Store plus 7 doesn't mean I was adding 7. Store plus 3 doesn't mean I was adding 3. 7 is just a key of memory. That's just where I selected that for memory, and I drew a diagram. 0, 7, and over here 3, so it looked like northing, easting. Northing was the cosine, easting was the sine. Then I put my angle in 0. I just store that as 0, because 0 sort of looks like the Greek letter theta, which represents an angle. So just memory things for me. and hopefully you could use it as well. So these are all angles and in hours, minutes, seconds, degrees, minutes, seconds, and we're going to convert them with the data collector. And this one will do it, the HP35S, and many good calculators will. The free 42S, and I know I say this just about every lesson, but it'll also do that. You convert, I think it's on key 5 is where you convert back in key 5, and then you got to go up here and look for HR or HMS and select whichever one of those you want. And failing that, this is how you convert over here. This is one of the things we did on our lesson the other day. I think we'll go ahead and go through that really quick. So I just picked out this angle here, 99, 23, 47. And anyways, to add all these angles, you've got to convert them to decimal degrees. And then when you're all done with when your finished answer, then you can convert back to hours, minutes, second. So we had this in an earlier class or an earlier lesson, maybe 5 or 6. I can't remember exactly which one. But to convert from degrees to hours, minutes, seconds to decimal degrees, and the reason I write HR because that's what it says in your thing. And mine just says HMS blue and HMS orange. So unless you're used to doing it, you're not going to really, it's going to confuse you for a little bit. But on the 42S, it has HMS and HR, and HR is the decimal, HMS is hours, minutes, second. A little easier to understand. So it's very simple, pretty simple process. So our angle is 99, 23, 47. So when you want to take the seconds and divide those by 60, you don't add the decimal, you don't need a decimal at this point, and you get 0.7833. Now you want to bring the 23 down and add those together, 23.7833, and you divide that sum, 23.7833 by 60, and you get 3964. Bring your 99 down, your degrees, and you got 99.3964. So that's your decimal degrees. When you get all done with that, if you want to change it back, here's your decimal degrees. We're going to change it back to hours, minutes, seconds. So we're 99.3964 right there. And now you just take that whole minutes and seconds. This time you want to use the 0.3964 times 60 is 23.7840. Now you want to just keep the 23 and bring it down. Now you want to take the leftover 0.7840, throw that over here, times that times 60. How'd that happen? Times 60. And that equals 47.04. Now what I've done here, I put a slash through the 04 because that's a carryover. This is 47 seconds, so 0.04. You just drop that. The only exception I would make is if this was, say, 47.99, I would probably round that up to 48. But keep in mind, this is in the seconds, 47 seconds, this is 7 seconds, 1 second plus or minus. Not a big deal because there's 3,600 seconds in every degree. So anyways, bring down your 23, bring down your 47, and you're back to 99, 23, 47. 99, 23, 47, 99, 23, 47. So if you don't have that convert factor in your calculator, you can still do this. You can still do that. You can add all these up, reduce them first, add them all up. All right, so we're going to go do that. We're going to go 99, 23, 47, 99.2347, and convert. So I got 99.3964. Now here's what I was talking about. There's two ways to do this. There's more than that probably, but you could store these now, go memory store, or else you can just run it without storing the memory. It's that simple. Store +1, and then just say store +1, whatever you want to do. We could do it both ways. And I'm using reverse Polish notation, so I'm going to go 108 plus instead of plus 108. So just keep that in mind. You would do it if you don't have an RPN calculator. If you have a normal algebraic calculator, you just add, and I do it a little different. So we have that number. Now we're going to go to 100.0815, convert, and I'm going to go plus. Now you would go plus and then put that in there. Okay, 247.0247, convert, and plus. 70, 20, 24, 70.2024, convert, and plus. 124.3953, 0.3953, convert, and plus. 71.5520, 71.5520, convert, and plus. 277.2024, 277.2024, convert, and plus. 89.0910, 89.0910, convert, and plus. And now I am 108, I'm that number right there, 1080-0000. Now, if you were in your digital and you wanted to convert to hours, minutes, seconds, you would hit convert back to hours, minutes, second here. And of course, it's going to be the same because we don't have any error at all. You're going to have error on traverses. This was a drawn up one, so you're not going to have any error on that. So, but anyway, so that's how you do that. You're going to find out you're going to end up with some kind of error there, and you're going to have to figure out what you want to do with that. With today's instruments, and like I say, a good adjusted tribrax. When I say adjust tribrax, I'm talking about the optical plummet plus the level. Same with your gun levels, everything level. You want to be able to set your tribrax on your tripod and have the next guy come and set it maybe backwards. It's still going to point straight down and won't be off the pin, off the point by a hundredth or two. That'll add up all the while. But anyways, that's how you reduce your traverse, and everything so far is just horizontal. I think that covers that. Now we're going to flip the whiteboard over, and we're going to do, as I promised, some vertical stuff now. Some trigonometry vertical. This whole traverse here, we carried coordinates, brought coordinates all the way around. And it was all two-dimensional XY coordinates, and now we're going to go to the Z coordinates on the other side. So bear with me. Okay, you will remember from lesson 4 or 5, we measured a tree height. We had solved right triangles every which way, and then we went into one lesson where we tried to use practical application of that rather than just an arbitrary. So we use right triangles to solve this. We hadn't got into zenith angles. We were still using right triangles as the Cartesian coordinate system, with 0 as the x coordinate and y as and 90 degrees. And then of course we're just the opposite of that. So let me go over how we first solved that. What we did is we said, okay, we want to measure that tree, and I said, okay, one way to do that is, and assume you don't have a prism, but you do have a tape rule or rag tape. It's a long 100 or 200 foot, like a nylon rag tape, and you can pull that out. So we pulled that out at a 90 degree, at a 0 or 90 degrees, however you want to refer that to right now. This is my pathetic drawing of an instrument. So that's how we measured this. We set up on the field outside of this tree here. We found a little knoll, and then we measured up here. This wasn't here at the time, so we'll just get to that in a minute. And then here are the two right. So we did a right angle. We went 90 degrees. Then we turned an angle up to the top of the tree, and that angle was 53 degrees. Now remember, this was 0 at the time. Let me just write this in. 0 degrees. And 0 also equals 90 degrees. 0 vertical equals 90 zenith. All right. So we turn an angle up to the top of the tree. We had this distance here, and so we calculated the height on that. And the way we did that was we were using right triangles. The tangent, we used tangent because that's the opposite over the adjacent. We had the adjacent, we had the angle. So the tangent of 53 degrees, and then we multiply that times the distance, 98 feet. And then we got 130.0504. That's from this point to the top of the tree. And then we turned this 8 degrees to the bottom down here. Then we used the tangent of 8 degrees times 98. And we got 13.7730. And then we added those two together, 13.7 and 130, and we end up with 143.8234. And that's how we solved that the other day on lesson 4 or 5, whatever it was. So that's two right triangles, and so that's what we did. Then we checked the math by using the law of cosines, in which we got into after this. After this, we started getting into oblique triangles, law of sines, law of cosines. Well, we also used in that first lesson, we introduced the law of cosines to solve this one. And we did that. So that was the law of cosines, a squared plus b squared minus 2 times a times b times the cosine. And then you want the square root of that. So I call this one a and this one b. So we call this angle C, and the opposite side is C. Okay, so a squared plus b squared is this number here, 36,310.7887. And then 2 times a times b times c. So 2 times that angle, or that distance, 2 times that. Oh, hold on, stop. How did we get these? Where did those come from? These are the hypotenuses of these two right triangles. Let's see, did I write that down anywhere? No, but we'll do it right now. So we have 53 degrees, and we want the cosine, because they connect right at the gun. So we want the cosine of that. 53 cosine, and that's 0.6018. But we know that's the longest, so like I went before, you just hit 1x, or you'd have to divide, but if you want to just keep multiplication going, hit 1x, and now times, so that's 1.6616, multiply that times 98, and we got 162.8407. That's where these came from. These are the slope distances. See, when we first needed to measure the tree, we didn't care about the slope distances. We used the tangent. Now we could also get that distance the same way if we wanted to, by using the sine of that. We could use 53 sine 162.8407 times is 130.0504. So I use the sine. The sine is the tangent is the t. It's the square. It's the right angle. And the cosine is where they connect, and the sine is what's left over. So the sine is the opposite over the hypotenuse. So we got that for both of those. So that's how we got those two hypotenuses. All right. So let's go back to our formula here. So 2 times a times b times the cosine ends up being 15,625 times 6,208. So 2 times that times the cosine is that. Now you want to minus that. So if you can't run that all on one equation like I can on this, or like the 42S can, you can just set this number aside, calculate that number, subtract it, and you're going to get this number here, 20685.609. And now you want the square root of that number. The square root of that number is 143.8234. And look at here, we have the same number there. Okay, so those are the two ways we've solved it. Now, the only thing with that, none of those give you elevations. They just give you the length of the trees, and that's fine. And now a surveyor is going to set up there, and he'll be able to measure that easy, and he'll also be able to give you elevations, but he's got to have, the gun has to have an elevation on it. So if you just walk out, set your gun down, and start measuring it, you're not going to have an elevation there. You're going to have to assume an elevation. Or if you find an elevation, if you happen to know that there's an elevation, if you've done your work and you've scouted around the area and you've seen what's there, you find that there's an elevation and you need the elevation, so you'll set that up where maybe you can see what's called a benchmark. So or the other way is like that, the traverse on the other side, you might be carrying elevations, and when you trav into this point here, you would have coordinates, x, y is coordinates and an elevation. But we're just going to assume you're carrying that gun out, you found a nice spot that sees the tree, but also sees a benchmark. And you have no elevation on here at all yet. All right, so you see there's a cul-de-sac. There's a big field here, and here's where the tree's going to fall. And over in between some houses, there's a cul-de-sac, and in the center of that cul-de-sac is a monument. So, and you'll see those if you ever start looking now that you're seeing all this stuff. It's a round lid about that big. Don't confuse it with a water valve lid or a gas valve lid. They look quite similar. This should be, here in the Pacific Northwest, just a nice smooth lid about that big around, has a hole in it that you can use to pull the lid off. And inside is a monument. It's a concrete monument with a brass disc on it. And that brass disc will have a punch or an X in it. That's because that's a specific spot on there. Now some of these are they have bearings and distances, as I showed you on the other plat map, to other monuments, so you can get bearings and distances. They don't necessarily have coordinates on them. In fact, they don't have coordinates on them. Not necessarily. They can though. But some of them are elevated. They have an elevation, and some of them don't have an elevation. They're only X, Y. Well, let's just say you go in to get your line out, and you're sent out here to do this guy's tree, and they say, I think we got a benchmark in the area. They will provide for you, or you'll have to provide for yourself. It's called a benchmark card. And over here in the Pacific Northwest, I'm just going to call this, we have a benchmark card. It says it's at this cul-de-sac. Well, I found it, flagged it all up, cleaned it out, put a tripod on it, and put a backside on it, put a glass on it so we can shoot it. And that is called, this is COR, that's called a benchmark number. COR stands for City of Redmond. Not necessarily where I'm at now, but let's just call it City of Redmond. And their number is 3928. That's just a random number I just pulled out. And the ortho elevation is 427.19. Now, I don't want to go that far into what ortho is, but here is, if you look it up, orthometric height. There's ellipsoidal height, geoid height, and orthometric height. For the sake of our argument, we're just going to call orthometric height is the elevation plus or minus sea level. All right, so that's going to be our ortho height. Another thing a bench card will have, it'll have accuracy, which I didn't write here. And it'll have a plus, minus, let's just say 0.02, so maybe 200ths. And that's what you can factor into too. So our ortho elevation on top of that monument, inside that case, is 427.19. So we've set a tripod on it, put a glass on it. Now we've measured down from the center glass of the tripod down to the monument, 512. So now we've taken those two elevations, 427.19 plus measure up. That's a measure up. That's not a V, that's a U. Measure up is 512. So our height of rod is 432.31. That's what that is, 432.31. So we have that. Now we've sat here and we can shoot at it. We can shoot it, and we can, what's called backing in an elevation. So let me take a few minutes here. If you're setting up somewhere and you see, if you're driving around, you see a surveyor set up, with their gun and their stuff, and they're shooting. Every time that gun already has a height on it. Every time it shoots, it's shooting to the prism, and the rod man is telling them what the prism height is, what the rod length is, and it's subtracting that to give you that elevation at the bottom of the rod, whether it be a ground shot or a curb shot or a monument shot or finished floor elevation, whatever it happens to be. That's just transferring your elevation from your gun to that using trigonometry. This is the same thing, only backwards. This doesn't have an elevation, but that does. So we're backing in the elevation to here. Okay, so we've shot this, and we have a zenith angle. So remember, zero at zenith, zero is straight north, and then you coming to the right, 90 degrees, 180, 270, and back to zero. And those all correspond with sine, cosine, cosine and sine positives, and so on and so forth. I already went through all that, so I'm not going to go through that again right now. So in this case, we have a zenith angle of 94, 25, 41. So I've already gone and I've converted it to 94, 42, 81. Now these over here, these are my little keys. Those are just represent my keys. So I had stored that in 7. I don't even know if I still got it in there. 94, 42, 81 I do. And then 0, I think I might have overwrote that. 94, 25, 41. Let me go recall. Let's go recall 7. 94, 42, 81. Okay, so this is the decimal version of it. Okay, so now we're doing cosine. We're doing the angle cosine. So we want the cosine of that angle. It's a negative 0.0772. And we we've measured to it, and the gun's going to give us the slope distance. We want the slope distance, 271.3916, and that's the times. So it is a negative 20.9534. So because it's a 94 degree angle, we know that it's lower than 9, so we've gone down. We're shooting down. So the gun's going to be higher. So that negative is going to turn into a positive. And that's one thing, if you're backing in an elevation, if you're shooting negative, you got to turn that to a positive. If you're shooting a positive, you got to turn it into a negative to add to your gun. So now we've got an HR, a height of rod is 432.31. And now we want to add this, because it's a negative, we want our guns higher. We want to add that to that, and that'll give us our height of instrument. So 432.31 plus 20.94. I've just done the math already. It's 453.26.34. That's the height of that instrument. That's the center. That's right where this crosses the center of that prism. The axis goes through there. And so wherever it's looking, well, let's just say if it's 90 degrees, which is flat, it's going to be, everything it's looking at is that height of instrument. Where do I have that? 453.26.34. If you have that set in 90 degrees, everything you're looking at is going to be exactly that height. Not factoring in earth curve, which that'd be a long look. We won't worry about that. So that's what that elevation is. So once that gun is set for that, it has its elevation, then it starts to, when it starts to measure, it starts calculating from there. So we are going to measure, we have that elevation now, and assuming that we have another benchmark, we will check in to confirm that elevation. That's good survey practice, not just to think that you're right. You'd also want to check in. If you couldn't check in right away, you might want to do a couple legs, backside that, and check in until you finally check in. But you do want to check in. That's kind of survey specific stuff. That's not really the math stuff, but it is. Okay. So we want to measure to the top of the tree. But this time we're going to actually have an elevation on the top of the tree, not just a length of the tree. So we're going to turn an angle up to the tree, which you already have. Well, we've turned this angle from 0 to 53. Well, we want the zenith angle. So 53 minus 90, so we know that it's 90 over here. It's going to give us 37 degrees from the 0, 37 in our cos. So we want 37 degrees. The cosine of 37 degrees times the length, 162.8407, and that's going to give us 130.0504. And now we want to add that to our HI. Yeah, we want to add that to the HI, and that's going to give us 580. It's going to give us right here 583.31. So let's just run that real quick here. 453.2634. That's our height of instrument, and now we've did the cosine of this length, and we've got 130. No. 34. Where am I at? Okay, enter. All right. 130.0504 plus 583.3138. 583.3138. So that's the top of the tree. 583.3138. So not only have we measured it, we actually have an elevation up there. Okay, now we're going to do the same thing with the bottom here. We have 8 degrees was this angle, this little angle here. When we calculated the right angle, we had 8 degrees. I guess you can see that. So we had 8 degrees, but we're starting at 90 degrees, 0, 90. So we're actually at 98 degrees. So we're going to go 98 degrees. Cosine, it's a negative 1392. And then we want 98631 times. I'm going to take the negative off. 98.9631 times 137730. So we'll add those two together now. So that's this distance, 137730 from this down. We'll add that distance. And then we'll get 430, yeah, and we'll add that. We'll subtract that from the gun, actually. So I guess I should have kept that as a negative. Let me just keep that as a negative. And do I have my height of instrument in there? I think it's recall 2 plus 439.4904. So I added that negative 13.773 to my height of instrument and came up with 439.4904. So that's the bottom of the tree where we measured. That's the top of the tree. Now let's do the math there. 583.3138, 439.4904, and the length of the tree is 143.8234. That's what we got from the law of cosines, and that's what we also got from our two right triangles. So I guess that's about it. That's what we've done. I'll give you a chance to take a screenshot of that. So we've solved that tree. Now, I guess one thing I want to say that's one of the reasons I'm doing this course is that very few surveyors would even do that much. They wouldn't do the right triangles. They're certainly not going to do, a lot of them can, some can't, law of cosines. But even this, where we've used the law, cosine to measure up there, with today's guns, you have a prismless feature. You can shoot, you can point it at anything if it's a reasonable distance, and that's easily a reasonable distance, and aim it to the top of that tree, the needle of that tree, and shoot the very top of it, and store that, and then shoot the very bottom of it, and store that, and then you just inverse those 2 points, and it'll tell you what the distance is. They don't need to know any of this math. And that's kind of the way the industry is going right now, is you're getting people that are surveyors, but they don't really, a lot of the newer ones, younger ones, are not picking up on that old school stuff. You had to know this in the old days. You didn't have all the data collectors with all the programs written into them, and you just, what we're calling button pushers now. You weren't just a button pusher. But if a surveyor goes out now and just shoots that and shoots that, that's just kind of a button push. You don't know what's going on. You need to know. In fact, we had a program in one of our calculators. It was quite a few years ago, and I did a trig loop with it, but I also kept all my zenith angles and all my distances. I wrote them all down in a book. That's another thing. We used to write everything down in a book, and it had to be legible, it had to be presentable in court, because a lot of times, or sometimes, if that was ever called into court, if there was a dispute, your notes was the evidence. So I did a trig loop with this new program we had in a new data collector, and we usually do differential level loops. I did a trig loop, and I went quite a ways and checked in, and it wasn't very good. I was like, I don't know what was going on with it. So I assumed I had made a mistake. So I just went and ran through all the numbers, just like we did there, the zenith angle, slope distance, backside that, and then when I got in, this time I checked in at just 100th or 2, so it was just fine. So what it was just a glitch in the software. So the point of all this is, if you don't know how to check, if you just accept that and say, well, no, I missed it by a foot or so, they say, well, go back now and do a level. You'd have to go back and do it over. You'd waste time, you waste the company's money. So if you know how to do your math, you can check a lot of stuff. I had another program that I was setting line stakes on the line. I had 1 point here, 1 point there, and there's a program you could just set your line stakes on a property line. And I went back into the office, and one of the guys says, why didn't you set these on the property line? I says, well, I did. He says, no, you didn't. And I says, well, I sure did. And I got my calculator out, my data collector out, and there's a graphic on the screen, and it showed him, and plus you can inverse line by point to line, and they were all well within tolerances. And he says, well, they're not. So we were kind of stymied, and turns out he made some calls and found out that that program had a glitch in it. It had a glitch in it, and they had to fix it, and after that we didn't have any problems. But if you don't know that, if you don't know how to check those things, you're just basically a button pusher, and you're just accepting whatever the machine tells you to accept, and you could end up with some really big problems that way. The whole company could cost you a lot. When we put in a vault, like a detention vault, sometimes those things are half of a city block. They're huge. They take crews almost all summer to excavate, to pour the foundation, to pour the walls, to do the whole thing. And if those are wrong, if your elevations are wrong, or if your dimensions are wrong, or something's wrong, that is why we have licensed surveyors. All that falls back to the licensed surveyors that work for the company. All that liability is carried by the licensed surveyors and the company that employs that licensed surveyors. So that could be $500,000 gone. It has to be ripped out, start over again. All that falls back. Not only will you have to pay that money, but you're going to lose your reputation as a company. You're going to lose it, and that contractor that's using you probably won't be using you the next time. So for any survey managers out there, or any company owners out there, it's really a good idea to have your surveyors be just as conversant and prolific with their calculators and being able to check these numbers as possible. All right, that's all I got for now. That's my soapbox speech, but yeah, I mean, that's it. So please like and subscribe, pass this around if you know other surveyors that could use this. If you're studying for an LSIT test, your PLS test, I'm going to be giving you more and more. I'm going to keep going more and more advanced all the time, and we're going to go through more heights, more XYZ coordinates. We're going to get into curves, things like that, and we're just going to keep going. Eventually, I'm going to get the LSIT test out here. We'll start picking out some problems in the test, and just continue on here and there to try to help everybody that I know, and my son's a surveyor too, to get your LSIT certificate, and then your next step would be your PLS test. So when you get that, you're sailing away. All right, please like and subscribe.